Yeah, so what happens as time progresses is that people, their enthusiasm is lost, and they kind of drift away from the course. So, and also another big problem with an NPTEL or any online course is that there is loss of this live interactions between the students. So a lot of the times people just a lot of the online courses, they lack these things like online session, the interaction session, which is a very important part of any learning. So you will learn more from interactions than simply hearing your teacher or your instructor. So interactions are a very important part of the of learning, and which is why this interactive sessions are actually offered. So uh, this time a lot of people have a lot of courses have online sessions, and I hope this online sessions will help you in the long term. So okay, fine. So I will start with that now. I hope everyone is able to hear me, right? Okay, fine. By the way, so there was one other issue with the meeting today is that, so I guess you all have received emails regarding the sessions today, right? So what happened today is that there are two sessions I think scheduled today. One is from 6 to 7 and the other is from 7 to 8. So that's a problem for this week. Yeah, Jyotish, you want to say something? Okay, so there are two sessions scheduled today. Yeah, Jyotish, you want to say something? Okay, fine. So next week onwards, that will not be a problem. So I will be rescheduling my sessions to a different day, and you will be notified about that. So okay, fine. So all the people are comfortable here with English, right? Oh, okay. That's good to hear. So I will start the session now. So I'll start my presentation now. So is my screen visible to everyone? Okay, fine. Okay, is it visible still? Okay, thank you. So okay, so this course, as you all know, this course is basic electrical circuits. So I guess some of you have some of you might have attended a session earlier this last week. I guess on Saturday was the first session, I guess. Some of you might have attended that session earlier. So anyway, so this course is about basic electrical circuits. This is a very basic course, and the target audience for this course is sorry, so people are joining. My screen is visible, right? I am sorry for getting or asking about the feedback, because that's one of the problems of online sessions, that you cannot see what other people are seeing. So I cannot see how you are seeing. That is why I have to continuously ask for your feedbacks. So excuse me for that. So anyway, this course is basic electrical circuits, and the instructor for this course is Dr. Ankush Sharma. He's a professor in Department of Electrical Engineering, IIT Kanpur. So yeah, so myself, I am Mayank Anupam, as I already told the people who have joined now. I am Mayank Anupam. I am a PhD student and a PMRF scholar at IIT Kanpur. I am also from the Department of Electrical Engineering. So moving ahead. So this week, the last week, you were all week 1 content was basically regarding the very basic stuff, basic circuit elements and waveforms. A lot of these things are already covered in your high school physics and all. So this was just a kind of refresher for you. Some new things you must have learnt in this in the week 1 contents. So I will quickly brush up these things for you. I'll summarize these things. Okay, so moving ahead. So you learned about electric circuits. So one small point that I would like to emphasize here is that, so electric circuits are what? They are like interconnection of elements with at least one loop, right? Hello? Yeah, so electric circuits are simply interconnection of elements with at least one loop. So this at least one loop part, this point, this is important because you see, if you have no loops and all, if you have just simple okay, this will be better with the pen. So suppose you have a voltage source here and you have a resistance like this and a resistance like this, and suppose this is open like this. What is the current going in that case? What is the current in that case? Yeah, current. So current is zero. So it's not of any interest to us, right? So it's a simple useless circuit, you can say. So it's not it's of no interest to us. So that is why this statement here is added, at least one loop. So when you have at least one loop in a circuit, so that circuit becomes interesting basically. So that circuit is worth analyzing. So that is why I have added this one small word here, at least one loop. So electric circuits are just interconnection of elements with at least one loop. Fine. So other things that you learned in this in the week 1 content was about charge and current. This is very pretty basic stuff. You must have learned it in your high school. So I will not go through it. Also, voltage. You also learned about what is voltage. So voltage is like work done per unit charge in moving it through an element. So that was what was told to you. So basically, voltage is like potential difference. It is the potential difference between two points. When you move a unit charge from one point to other points in an electric field, you do some work. So that work is defined as a potential difference of the voltage between these 2 points. Okay. Now you also learned about power and energy. You also learned about some basic circuit elements. So what are those circuit elements? Okay. So you also learned about sinusoids. So yeah. So before asking about that, before going about that, I want to ask why do you learn about sinusoids? Can someone volunteer? Why do you learn about sinusoids? Hello? Can someone volunteer? Okay, so what else? It's true, that is easily it can easily be generated. That is one of the biggest reason that you are learning about sinusoids, and that is why we are interested in sinusoids. Other reason? Any other reason that you might know? Any other person would like to volunteer? True. True. Yeah. So basically, the signals that will the things that we'll be concerned with will be time varying, right? So, but there is one very crucial point. Other than the fact that sinusoidal this thing are easy to generate, that is one point. But there is one another point also. Yeah. So I think some. Well, that is not actually true. So we'll come back to this point. Actually, it's not actually true. So there is a okay. So I think some girl was trying to say something. Yeah, right. What is it? Can you tell? No. So can you tell the name of that? So I want to hear a term here. So what do you say? So you are saying that waveform of any particle can be expressed as sinusoids. You are saying, right? Correct. So do you know what is that called? Means okay. So let me save you the trouble. So this is like so basically sinusoids are important or interesting for their for basically two reasons. So I'll tell you that. Uh, okay. So this is visible, right? Here, everything. Hello. It is visible, right? Okay. Thank you. So okay. So sinusoids here, they are interesting for basically two reasons. The reasons are this one. So basically, any sinusoid that you are interested, any signal that you are interested, are generally for us they will be periodically time varying in nature. Okay, so they will be periodically time varying in nature. So all those signals, they can be expressed as a sum of a lot of sinusoids of different frequencies. So this is called as Fourier series representation. I think all of you must have heard it somewhere. Fourier series representation. Have you heard this term, Fourier series? Correct, correct. So Fourier series of those people who do not know, it's okay. It's not important for this course. It's just that Fourier series, they are like you can represent any signal as a combination of a lot of sinusoids of different frequencies. So that is why we are interested particularly in sinusoids. So other reason was that generation of sinusoidally varying currents and voltages is very easy. So that was already said by one of your peers. So these are the two main reasons that we are interested in sinusoids. So moving ahead, when we learn about sinusoid, you also learned about phasors. This must be a new thing for you. Phasors. Phasors is not talked about in high school physics. Phasors is a new thing. So phasors. Why do we need phasors? And what is so interesting about phasors? So again, anyone would like to volunteer about it? Yeah, correct. So basically, okay. So basically, phasors, they are you know what happens is that a lot of times we are not actually interested in exact waveform of the signals. So most of the times we are not we are not interested in the exact waveform or exact time dependence of a signal. We are only interested in the phase difference, or the basically as your peers said, we are interested in their delays, or what is more delayed than other, the relative difference between the signals. We are more interested in that. We are not exactly interested in the time domain representation of that. So this is where phasors actually help us. So the assumption here is that basically phasors how do we write something in terms of phasors? We say that any signal, that is, suppose this is here like cos omega 1 t plus theta 1. So what will be the phasor representation of this? It will be some simply, so magnitude here is, assume magnitude is 1, so it will be 1 angle theta 1, right? That will be the phasor representation of this particular voltage signal. So here we are ignoring the fact, we are like ignoring the dependence on time dependence part. We are ignoring that dependence here. Why we are able to do that? Because we are saying that two voltages, if we are comparing two voltages or two different physical quantities, we are saying that these two quantities can be compared in terms of their phases, because we are assuming that they are generated from the same source, or basically their frequencies are same. So that is why I have mentioned this in red. So this is very important point. So comparing two or more different quantities based on their phasors makes sense only when they are generated with the same frequency. For example, if V1 is equal to cos omega 1 t plus theta 1 and V2 is equals to cos omega 2 plus theta 2, then they cannot be compared through their phasors as the frequencies are different. So what happens when you try to write it in terms of its phasor? So V1 will be, so okay, so in this case what happens is that your V1 is equal to cos of omega 1 t plus theta 1, right, and V2 is equal to cos of omega t plus theta 2, omega 2 t plus theta 2. So its phasor representation will be V1 is equal to what, 1 angle theta 1. Its will be V2 is equal to 1 angle theta 2. So but these two phasor representations, they cannot be compared. Okay, they cannot be used simultaneously, because when you write a phasor representation of a particular signal, there is an underlying there is an implicit assumption of a frequency associated with it. So you assume that frequency here is omega 1 and you assume your frequency is omega 2. Since these two frequencies are not same, you can never compare them when you are trying to do analysis. So this is a very important point, that two or more signals, they cannot be compared in terms of their phasors if their frequencies are different. Okay, so moving ahead. So after that you also learned about basic circuit elements, like yeah, so you also learned about basic circuit elements like resistors and capacitors and all. So this is pretty basic stuff and I will not be going into it. So an important point about capacitor I would like to mention here is that you all know that current through a capacitor is equal to I times I is equal to C dV by dt. So this is basically proportional to the derivative of the voltage across it, right? So but what happens is that, so because of this relationship, what happens is that for a given finite current, if the current through the capacitor is known to be a finite value, you cannot abruptly change the voltage across it. So otherwise this derivative function, you must know that that the derivative, okay, sorry, yeah, so you must know that the derivative, when you take the derivative of any abrupt change, like suppose what I meant by abrupt change, so this is like, sorry, ignore this. Suppose this is time domain, this is voltage. So suppose a voltage suddenly changes across the capacitor. Suppose this is the voltage across this capacitor. See, this is suppose plus minus V. This is the voltage across this capacitor. The waveform is given like this. So suddenly at t is equal to 0, at time 0, it suddenly jumps here. So what is the derivative of this voltage waveform? So I am asking about dV upon dt. What is that? If there is a sudden jump, no. At this point, derivative becomes infinity, because there is a sudden jump. What is meant by derivative? Derivative is what? Rate of change of something, yeah, with respect to the other given quantity. So dV by dt represents rate of change of voltage with respect to time. So here you can see that voltage has suddenly changed. In very infinitesimal time, in a very small instant of time, voltage suddenly changed to a large value, from 0 to a different value. So this is like a large change in a very small time. So hence you can say that this is infinity. So as I pointed out, so the current through your capacitor is finite, it's some finite value, then definitely your this LHS, if your LHS is finite value, then your RHS cannot be infinite, right? So that is why I say that the voltage across a capacitor cannot change instantaneously or abruptly when the current through the capacitor is finite. Okay, also the current through capacitor is zero in steady state, in DC steady state. So basically what I mean by that is, okay, what I mean by that is the following. Suppose you have a circuit, some resistor, some capacitor like this. Okay, so this is the symbol, by the way, this is the symbol of ground. So I think all of you know that. Okay. So what happens in this circuit? Suppose I turn on this circuit, I turn on this voltage source. So initially what happens is that this capacitor will start to get charged, right? This capacitor will start charging. After some time, it will be fully charged, and the voltage across it will be same as the voltage here. So if it is V, it will be V also, and the current through it will become zero. So this is what I mean by saying that capacitor, the current through a capacitor is zero in DC state, DC steady state. In DC steady state, what happens is that, what I mean by DC steady state is that the voltage through this capacitor, voltage across this capacitor will not be changing. That is meant by the steady state. So in that case, the current through it will be zero. So this can also be verified from this expression here, I is equal to C dV by dt. If the voltage is not changing, then this will be zero, and hence I also is zero. Okay. Then we moved ahead to the inductor. So inductor also the same thing. Inductor's relationship is given like this. So in this case also, the voltage is given as the time derivative of current across it multiplied by the inductance. So here also, if the voltage across the inductor is finite, if the voltage across the inductor is finite, the current through it cannot change instantaneously. It's the same concept like capacitor. Also, as I said in the capacitor, the current is zero in the DC steady state. Similarly, in the inductor, the voltage is zero across it in the steady state, in the DC steady state. So this is already known to a lot of people, because this is all covered in also covered in high school physics. Okay. So other two things that I added here, which was not covered in the week 1 content, was regarding voltage source and current source. So what is a voltage source? Voltage source is anything which will maintain a constant potential difference across it, irrespective of the current flowing through it, right? So if you are given a voltage source of value V, so what happens is that across its terminals, it will maintain this constant voltage. Doesn't matter what is the current passing through it, right? So its characteristic is like this. So IV characteristic, if I plot, so voltage is constant for any current, isn't it? Similarly, for a current source, it maintains a constant current across it, irrespective of what is the voltage across its terminals. So here, suppose current is I0, so it will, same amount of current I0 will be passing through these two terminals, and it doesn't matter what is the voltage across it. So its IV characteristic is given like this. So this is I, this is V. Current is like this. It will be constant. Doesn't matter what is the voltage across it. Okay, moving ahead. So then you also learnt about Kirchhoff's circuit laws. You learnt about Kirchhoff's current law and learnt about the Kirchhoff's voltage law. So you know that Kirchhoff's current law says that current entering or leaving a particular node, the sum of all the currents entering or leaving a particular node is zero, right? So this is basically a result of conservation of charge. So if you have a particular node, if you have a lot of branches coming out like this, the current through all of this, when you sum, current entering all of this will be 0, the sum of all the currents, simply because a second. Yeah, simply because why? Because you assume that at this point, at this node, all the there is no charge accumulation. So what will happen if the current entering, the sum of all the currents entering this point will not be 0? There will be residual current, right? Basically the current, when the sum is non-zero, there is some finite amount of current which is going inside always, and it is not leaving, it is not coming out anywhere. So there will be charge continuously accumulating here. So that assumption is made that you are not accumulating any charge anywhere. This is why I have highlighted this point here, that charge is not accumulated anywhere in the circuit. This is the assumption basically. Because the small caution here is that this Kirchhoff's current law is strictly valid only when the circuit dimensions are very small compared to the wavelength of the signal. So this will be something which you will be learning later on if you take some higher level courses. You will be learning about transmission of volt or power through very long power lines. You will be learning these things there. So you will see that basically current entering here and current leaving here, they are not the same. So there you will feel that Kirchhoff's current law is not valid there. So I just wanted to mention this point here, that Kirchhoff's current law, they are strictly valid only when the circuit dimensions are greater than the circuit dimensions are smaller than the wavelength of the signal. Okay. So again, yeah, hello. Okay, so okay, so the point here is that you know that there is time varying nature of current, right? Current is like this. Suppose a sinusoidal current you are sending. Okay, so what happens is that if the circuit wavelength, if the length is so large that the current here is suppose you are sending a sinusoid like this, right? So suppose the current here is this upper part of the sinusoid, okay, but current leaving here is the lower part of the sinusoid. Then definitely the current leaving and current entering are not same. You understand what I am saying? No. So true. So what you are saying is true. You see, what you are sending here, at the same point of time. So when you are saying that the current entering and current leaving are same, it is assumed that the time that you sent some charge here, an equivalent amount of charge is pushed out of here, right? But that is strictly true only when the current is basically a DC. For a DC it is true. Basically for a DC, when you send in some charge here, equivalent amount of charge is pushed out of this other node, other part of the wire, right? But when it is a sinusoidal current like this, and the wavelength of this sinusoid, if sinusoid is if suppose your wire is like this, but the sinusoid is like this, it is varying over a very long thing. Basically the wavelength is much larger compared to your dimension. So there also it is valid that whatever current will leave here, current will enter here, same amount of current will leave here, because you see current at this point and this point are same. From the waveform also you can see, you see the waveform. But if the current waveform is like this, suppose, so you can see that the current entering here and here are not the same. You understand what I am saying? Yeah, so that is what I meant here. Are you clear now? Hello? Are you clear? Hello? Hello? Uh, Hello. I'm sorry, guys. So there was an internet connection problem at my end. I am very sorry. Uh, okay. Okay. So by the way, the guy who was asking me the question regarding this uh, Kirchhoff's current law, are you clear now? Is the doubt clear now? Actually, antenna also is the same thing. So basically, you see antenna, it's modeled like this, right? So it's actually more related to electronics. So what happens is that you see antenna is open, right? Antenna is open, but you see here current is going. Antenna is modeled in this way. So antenna is open at one end, but it is connected to a circuit at the other end. So there is some current which is going inside the block here. So how is that current coming? Where is that current coming from? Because this is open here, isn't it? But there is a current going here. So this is like Kirchhoff. You will feel that Kirchhoff's current law is not valid. So this is because of these things, that wavelength and all. You have to be careful when you are analyzing circuits with where the signal wavelength is much smaller compared to the dimension of the circuit itself. Okay, so moving ahead, Kirchhoff's voltage law. You learned about the Kirchhoff's voltage law. Okay, so there you learned that the algebraic sum of the voltages across the elements in the loop is zero. So it's a result of the conservation of energy. So you know that basically analogy you can draw from the point that if you are starting from a particular point on the ground, then you go to a different point here, and to come back again here. So basically, when you travel in the loop here, the energy gained by you or the work done by you will be zero, isn't it? The net work done is zero. Hello. Right. So that is the from the same analogy you can also so basically that is the analogy for the Kirchhoff's voltage law. So that is why you say that in a loop the voltage across the sum of all the voltages is actually zero. So here also the assumption is that your circuits are not very large compared to the basically the circuits are compact, and the magnetic field is not cutting through your circuit, through your loop. Basically what I am saying is that if suppose this is a loop, and suppose there are magnetic fields cutting your loop, so then this assumption is not actually true. This Kirchhoff's voltage law is not strictly true in that case. You have to modify your Kirchhoff's voltage law in that case. So back EMF, you must have heard about back EMF or things like that. So in standard 12 physics you must have learned those things. So you have to introduce those terms to make sure that Kirchhoff's voltage law holds there. Okay. Okay. Okay, why is that happening today? Sorry, so I don't know why is this happening today. So the network is very good here. Okay, so I was saying that the algebraic sum of voltages across all the elements in a loop is zero. So this is what Kirchhoff's voltage law says, and this is a direct result of the conservation of energy. How is that? So one analogy that I said is that when you start from somewhere on the ground, when you are standing somewhere on the ground, and you start from there and you start moving across went up some building, then went up another building, then came down, and finally reached the same point, then basically the energy gained by you or the work done by you will be zero, isn't it? If you start from some point and come back to the same point, the work done by you is zero in that case. So similarly you can say that Kirchhoff's voltage law, based on the same concept also, Kirchhoff's voltage law says that the algebraic sum of all the voltages across the element is zero, because the voltages here is what? It's a potential difference, isn't it? Potential. Here also when I am saying that work done is zero, it's in terms of the gravitational potential, isn't it? You are sitting here, then you went up someplace, you gained some potential, then you went again up, you gained some more potential, but then you came down, reached the same point. The net total potential gained by you is zero. Same thing is said by this Kirchhoff's voltage law also. So then again, after that I said that you have to be careful when dealing with circuits, which when dealing with loops which have some magnetic field passing through it. So when your loop is when you have a loop and there are some magnetic fields passing through it at that particular time. So are you with me? Am I audible? Yeah. Okay. So when you have a circuit like this and you have a magnetic field passing through it, then in that case Kirchhoff's voltage law doesn't seem to hold as it is. You have to introduce some other terms to make sure that Kirchhoff's voltage law holds in that case. So that is why you introduce some terms like back EMF or induced EMF, something like that. So they are introduced in order to make sure that your Kirchhoff's voltage law holds there. This you must have heard in your must have learnt in your class 12 physics. I am just reiterating that. Okay. So after that you learned about series and parallel combination. So this was pretty. I will simply, this will basically, these slides I think will be available to you, so you can go through this. So this is just a summary of what you learned. So okay. So then you learnt about voltage current relationships in terms of phasors. So for a resistor, this okay, so notice this voltage and current, V and I, they are written in bold. So when I write something in bold, it means that I am talking about their phasor and not the time domain signal. It's a phasor representation of the voltage, and this is phasor representation of the current here. So for resistor, V is equal to IR volts. For inductor, V is equal to I into J omega L. So basically this was explained very well in the content that was shared in the week 1. Similarly for the capacitor, this becomes I into 1 over J omega C. So here this J omega L, 1 over J omega C, they are like impedances, isn't it? They are just like, if you replace this R with J omega L, you get, so basically this J omega L, 1 over J omega C, they have the same dimension or unit as, this R resistor. So they are in some terms representing the resistance, but they are not the typical resistance that you see. So that is why they are called impedances. Impedances are what? Impedances are frequency dependent in general. So this is written here. So all the above equations that you see here, they can be represented in terms of Ohm's law, like this. V is equal to I times Z. But this Z here will not be a pure resistor. It will be a something which will be acting kind of like a resistor, but it is not a resistor, because it is complex in nature. It is in general complex, and that is why we give us a different name to it. We say that it is the impedance of the element, and it can be frequency dependent. So you see here Z is equal to J omega L. Z is equal to J omega L. So this is clearly dependent upon omega here. Similarly here Z is equal to what? 1 over J omega C. Here Z is dependent again upon the frequency. Also other point is like given here, Y is 1 over Z. So you know that for R you also say that if you invert it, you get 1 over R is equal to conductance. What does this quantity represent? G. This like resistance, it signifies the resistance to the flow of current. So that so if you want to invert the resistance and get conductance, what you will say? You say that conductance is something which facilitates the conduction of current. It basically facilitates the current it makes the make sure that the current is flowing easily. So if the conductance is high, current can flow easily. If the resistance is high, current will feel difficulty in flowing. So that is how these terms are defined. Then you learnt about the very basics of power. So power was just introduced. You learnt that instantaneous power is what? Vt times it, the voltage into the current. You also learnt about average power. How is it defined? It is basically the time integral divided by the total time that you considered while integrating it. For sinusoidal voltages and current, average power was found out to be like this, as was also mentioned in the content, week 1 content. So, okay, yeah. Come again, I couldn't hear you properly. Yeah. No, that is not called average power. So average power is Vrms times Irms into cos of theta V minus theta I. This is average power. So you also have to multiply with this particular factor here. So you will learn in the week 2 content that this factor is called power factor. So this basically says that how much real power, how much actually the power you have wasted. So Vrms times Rms is not the actual power, it's the apparent power. So you'll feel that this much power is lost, but actually the actual power is given by the whole term. You have to also multiply with this cos theta V minus theta I. So that is giving the actual power. Okay, this is called the power factor, theta V minus theta I. This is called the power factor. You also have to multiply using this. Multiply this factor and then you will get the real power. Okay, so I went through the okay, so I went through the content, week 1 content. I also went through the assignment. So okay, so I went through the week 1 content. I also went through the assignments, and I saw that there were some questions related to RMS power and power factors, I think. So what is the deadline, by the way, of submitting week 1 assignment? Hello? Yeah, I am sorry. I don't know what is happening today. So, okay, anyway. So, I was asking that what is the deadline, by the way, of submitting week 1 assignment? Hello? Yeah, so okay, so someone is asking me, can we get the recording of this? So yeah, so I will be uploading this on my YouTube channel. So link for my YouTube channel, I can give you the link of my YouTube channel. So there you can see. So on my YouTube, I will be posting these recordings on my YouTube channel. So there you can see the recording. So I don't know what is happening today. So network generally is very good here. So I am sitting in IIT Kanpur only. So network generally is very good, and we never have any complaint regarding it. So I don't know what is happening today, or why is this misbehaving like this. So I was asking, by the way, that what is the deadline of submitting the week 1 assignment? August 10th. Okay. So yeah, so there were some questions in week 1 assignment which were related to RMS power and power factor and all. So these things are discussed in the very first lecture of the second week. So you week 2 content basically. So you can go through that. If you have any difficulty after that, you feel free to ask us. You post your doubts in the discussion forum. So by discussion forum I mean there is an option called ask a question in the NPTEL portal or SWAYAM portal. So there you can post your questions. We will be answering it in our discussion sessions. Yeah, I will. Okay, I can join that, but it will be better for everyone if you join that. If you post your questions on the discussion forum, ask questions thing. No, you can ask your questions. So yeah, that discussion forum, that is meant only for discussing the content of this course. But if you have some doubts, and if the TS feel, they can answer there also. Okay. By the way, I will join the WhatsApp group that you are suggesting me to. But that will be a good for the discussion forum that is made specifically for this purpose only. So post your questions there. That will be benefiting everyone. So everyone can see there and can learn from there. Okay. Okay. So I would like to now get a feedback from you regarding this the content that I presented to. So do you have any doubt, anyone else in that content? So I will be sharing again 1 second. Yeah, so in everything that I talked about, so do you have any doubt here anywhere? Okay, delete it. Do you have any doubt here? Hello? Anyone has any doubt in the content that was covered today? Okay. So pardon me for the internet connection. I assure you that this will not happen from next time. So I don't know why this was happening. Generally the internet connection is very good here, and I don't know why this happened today. So okay. So other than that, I also wanted to discuss some questions with you. So is my screen visible? Okay, fine. Okay, fine. So here basically this is a simple question regarding, you have to find the total average power absorbed by a 2 ohm resistor when the voltage waveform shown in the figure is applied across it. So you are given the voltage waveform here. The voltage waveform is here, and this voltage waveform is applied to so this is something of this kind. This is 2 ohm resistor. This is the voltage waveform applied across it. Okay. So you are asked to find the average power absorbed by this 2 ohm resistor. So how will you do that? So I want you folks to try this. Tell me, what should I do? Hello? So anyone, what should I do? How should I go ahead? How should I proceed? Okay. So basically what we do in this case is that, so you know that so forget about this RMS term here. So what is the average power? The formula of average power, it is the time integral of V square, right? It is the time integral of V square. So let me go back. Yeah, average power is this, right? It's the time integral of instantaneous power and divided by the total time, isn't it? So what is the average power dissipated in the resistor? If it is a resistor, what is the average power dissipated? So for a resistor Vt, for a resistor, what is, sorry, yeah, for a resistor, what is the average power Pt? The formula is Vt times It, right? This is the average power, this is the instantaneous power. So for a resistor, what will this become? This will become Vt times It becomes Vt upon R, isn't it? So this becomes V square T upon R. Okay, and now you have to integrate this. So basically, for finding the average power, what you need to do, you need to integrate this V square T dt divided by R, and you have to divide this by the time period of this particular thing. You have to integrate it in zeros to time period. What is the time period, by the way, here? Okay, so what is the time period of this particular signal, of this particular voltage waveform? Correct, exactly. So you notice that this is a periodic signal, periodic waveform, periodic voltage waveform. It is repeating itself after every 5 seconds, isn't it? You see, it is repeating itself after every 5 seconds. So the time period of this particular waveform is 5 seconds. So t is equal to what? 5 seconds. So you have to integrate this particular voltage V square T upon R, and then divide this by the total time that you took for integration. Then you will get the average power. So this is what is done here basically. So ignore this V square thing, RMS term. So don't get confused with this RMS. Since you are not taught about this, it's better not to mention this. So it's just V square, which is integrated from 0 to 2 second first. So this is the simple integration. What is this line here? What is the equation of this line? It is a straight line, and it is starting from 0, going to and then going to 8 volt in 2 seconds. So this can be presented as 4t, isn't it? Okay. So basically what happens is that this is the equation of this particular, so a particular voltage waveform for 0 to 2 seconds, and you square it. So the formula is what? Formula was V square T dt. So that so first you find out this. So V square, you first find out this integration of this from 0 to t. So 0 to t you cannot directly integrate it, because this voltage waveforms, this is other type of voltage waveform. This is a different type of voltage waveform. So you break it in two parts while integrating. So you integrate from 0 to 2 seconds for one particular type of voltage waveform, which is given by Vt is equal to 4t, square it. Then you integrate for other type of voltage waveform which is given from 2 to 5 seconds, which is 0 simply. So when you integrate it, you will get this V square is equal to 8.533. Okay, and what was the resistor value? It was 2 ohms. So basically the power is what? Power is the integral that you found out here divided by the resistance value. So this will become 4.267 watts. So any doubt in this? Hello? Hello? Any doubt in this? Oh, okay, fine. Okay, great. So other than that, there was another problem, which was to find out the total equivalent impedance between these two terminals. So can anyone attempt this question? Can anyone say what to do? What should we do in this question? Can anyone attempt? Correct. So how do you proceed? What should you do? Correct. You have to find out. So basically, the general procedure is to first find out. First look for whether something is connected in series or not, or parallel or not. So that will simplify your job basically. So here you can see that this resistor you see one terminal is here, one terminal is another terminal is here. But for this particular resistor, this particular impedance also, one terminal is here and another terminal is here. So these two impedances are in parallel, isn't it? Because they are both the terminals are connected together. They are shared. The same terminal they are using. Similarly, you can see that this impedance also, one terminal is here, other terminal is here, which is kind of the same thing. So let me mark also. What I am saying is that you see this terminal and this terminal for this particular impedance. So this you have to basically see that two elements are connected in parallel when they are both the terminals are connected to the same potential, isn't it? So here you see that for this impedance also, its one terminal is connected to this point and other terminal is connected to this point, but this is a simple wire. So basically these two are shorted, isn't it? These two are short. These two terminals here and here, they are shorted. So that is why these two impedances, they are in parallel. Similarly, you can say that this is also in parallel with the other two. Similarly, this is also in parallel with the other three. So basically all these four impedances, they are in parallel. So the net total impedance will be given by what? So if I want to write the equation for this, so 1 by Z equivalent is equal to 1 by Z1 plus 1 by Z2 plus 1 by Z3 plus 1 by Z4, isn't it? So this is how it is found out. So this is done in this this is what is done here. So this is how you found out the equivalent impedance. When you do this, you can manipulate the algebra and then you will get this answer. So this was easy. So any doubt in this question? Hello, any doubt in this question, anyone? Okay, fine. Okay, so I guess that's it. That's it for today. Okay, I guess that's it for today. So if you have any doubt in the content that was covered today, you can ask those questions in the discussion forum that is offered by NPTEL. So we will be happy to answer that, or you can also ask those questions in the next discussion session. We will be answering those questions. So couple of things. So basically this was the first week, so I covered a lot of theory. So this session is not supposed to cover theories. It is only these sessions are provided only to discuss the sample problems. Basically I have to solve the questions, and meanwhile I also teach the concepts to you. So that is what these discussions are primarily aimed for. So this was the first week, so basically we cannot frame a lot of questions, right? So the first week content was not very favorable to framing questions. That is why I also went through I also framed some concepts. So I hope you understood something, you learned something from today's discussion session. So next time onwards it will be mostly problem solving. So you can also bring your questions, if you can also bring your problems if you have any, and we will be happy to discuss that in the discussion session. Okay. Okay, so and yeah, so other thing is that the discussion session today happened on, so I took my discussion session on Monday, right? Today's Monday, 6 to 7. But most probably next week onwards, my discussion session will be on Sunday, 5 to 6 or 7, 6 to 7, in that time period only. So you will be getting a notification about that from NPTEL team, the change in time slot. So hope to see you in large numbers next week on Sunday. So, okay, that's it from my side. Thank you for coming. Thank you for joining the session today. Oh yeah, YouTube session. Okay, so YouTube. Okay. 1 second. I forgot about that. Hello. Okay. Yeah. So this is I have shared a link, YouTube link. So this is the very first week 0 kind of preparation kind of stuff. So from here you can reach my channel. So there I will be posting all the videos every week discussion. You can watch. You can go through those discussion sessions. And PDF. I am sorry, but this I will be uploading my PDF. I will be giving my PDF to the NPTEL people. So I'll have to confirm from them whether that has to be dispersed to you or not. So that has to be confirmed from them. After that, I'll be able to give any response about that. So can any one of you please confirm whether you got the YouTube link or not? Okay, so can you quickly click and see whether it is going to the right place or not? It is linking to the right place or not? Hello, can anyone please click on this link and tell me whether the link is opening or not? Okay, fine. Thank you. So that's it from my side, and hope to see you in large numbers in the next discussion session. That should be on Sunday, most probably. So see you. Bye bye. Thank you for coming today.